Hello students, as I already explained in the last video, there are two major approaches in deriving Michaelis Menten equation. One is rapid equilibrium approach. It is given by Leonard Michaelis and Menten in 1930, and the second one is steady state approach. It's given by George Briggs and Haldane in 1925. The equation derived by Michaelis and Menten was not applicable for all the enzyme catalyzed reaction. So it was modified by George Briggs and Haldane, and they introduced a more generally valid assumption that is called steady state assumption. Okay. If you wish to learn the derivation by rapid equilibrium approach, you can refer my previous video. In description also I have given the link for the rapid equilibrium approach. Okay students, now we will see the in steady state approach in detail. In steady state approach also we are going to relate initial velocity and substrate concentration. Okay, this is also for single substrate enzyme catalyzed reaction. That is, your enzyme has only one substrate binding site. Okay, so only one substrate can bind with the enzyme at a time. So let us consider the two basic steps of single substrate enzyme catalyzed reaction. So first, your enzyme combines reversibly with the substrate to form an enzyme substrate complex. So here the rate constant for the forward reaction, that is for the formation of enzyme substrate complex, is K1. Okay, and rate constant for backward reaction is K minus 1. Okay, then this enzyme substrate complex breaks down to form enzyme and the product. So here the rate constant for the forward reaction is K2 and rate constant for backward reaction is K minus 2. So if you combine these two equations, you will get this equation. We are investigating the experiment at the initial period of time to study the effect of substrate concentration on the reaction rate. So here at the initial period of time, your concentration of product is very low. So the formation of enzyme substrate complex from the product can be ignored. That is, you can ignore the backward reaction. So K minus 2 is negligible at the initial period of time. So consider this is equation number 1. So you can write this equation 1 as enzyme combines with substrate. It forms enzyme substrate complex and it gives enzyme plus product. So let's start deriving the rate expression. So the first step is initial velocity, that is initial rate or velocity V0 is equal to rate of product formation. So rate of product formation, how you will write? So you have two parameters here. So for that, first you have to write the rate constant. So K2. So for rate, and second term is your concentration of reactant. So here the reactant is enzyme substrate complex. So initial velocity V0 is equal to rate constant K2 into concentration of the reactant, that is concentration of enzyme substrate complex. Okay, so V0 is equal to K2 into ES. So this is your equation number 3. Then in equation 3, the concentration of enzyme substrate complex is not measured experimentally. So we have to replace this term with easily measurable quantities, that is the enzyme, total enzyme concentration and initial substrate concentration. So Briggs and Haldane made an assumption that is called steady state assumption. This steady state assumption is usually established within milliseconds of the start of the reaction and is maintained for a few minutes until there will be increase in the product concentration. It means there will be a enzyme substrate complex formation and it is maintained at a steady state. That means it would be breakdown down as fast as it was being formed. Okay, so at steady state, your concentration of enzyme substrate complex is constant. That means the rate of formation of enzyme substrate complex is equal to the rate of breakdown of ES. Here, your enzyme substrate complex is breaking down in two ways. Okay, so one is your enzyme substrate complex breakdown into enzyme and substrate, and in another way, your enzyme substrate complex breakdown into enzyme and product. Okay, so this is the difference between your steady state approach and rapid equilibrium approach. In rapid equilibrium approach, they won't consider this breakdown step. They will consider only this first step, that is there will be a equilibrium between enzyme substrate and enzyme substrate complex. Okay, so here in the rate of breakdown of ES, they will take out only this term, that is K minus 1 into ES and this K1 into E and S. But in steady state approach, we are writing the rate of breakdown of ES as both the steps. Okay, we are including both the product formation. Okay, that is the positive point of your Briggs and Haldane. Okay, so now you write the rate of formation of ES. Okay, so here rate constant is K1 for rate of formation of ES, and the concentration of reactant is your enzyme substrate. So rate of formation of ES is equal to rate constant K1 and concentration of enzyme and concentration of substrate. Okay, so that is equal to the rate of breakdown of ES. So in the first step, the rate constant is K minus 1, the reactant is concentration of enzyme substrate complex, plus second way the rate constant is K2 and the concentration of reactant is ES. So K1 into E into S is equal to K minus 1 into ES plus K2 into ES. Okay, so K1 into E into S is equal to ES into K minus 1 plus K2. Okay. So separate the constants from the variables, so you will get E concentration of substrate divided by concentration of enzyme substrate complex is equal to K minus 1 plus K2 divided by K1. Okay. So this is equal to your Km, nothing but Michaelis constant. Okay. Now we introduce a total enzyme concentration because it is the known quantity. So during the course of reaction, your enzyme is present in two forms. That is, it may be present as a free enzyme or it may be present as a bound enzyme. That is, your enzyme bind with substrate and it forms enzyme substrate complex. So if you want to calculate total enzyme concentration, you have to sum up free enzyme and concentration of enzyme substrate complex. So from this you can calculate the concentration of free enzyme. So concentration of free enzyme is equal to total enzyme concentration minus enzyme substrate complex. So consider this is your equation number 4 and this is your equation number 5. So equation 5 in 4. So E naught minus E S into S, okay, divided by ES. You can write it as Km. Km into ES is equal to E naught into S minus ES into S. Okay. So now you calculate the concentration of ES. Okay, so Km into ES plus ES into S is equal to E naught into S. Okay, so from this, okay, so ES is equal to ES into Km plus S is equal to E naught into S. So ES is equal to E naught into S divided by Km plus S. Okay. So this is your equation number 6. So you just substitute this equation 6 in equation number 3. V naught is equal to K2 into your enzyme substrate complexes E naught into S divided by Km plus S. Okay. So this is your equation number 7. So where K2 into E naught is equal to V max. Okay. So here your V max is nothing but maximum velocity. So what is maximum velocity? So when the substrate concentration is very high, all the enzyme is present as enzyme substrate complex. Okay, there is no free enzyme in the reaction. So all the enzyme is present as enzyme substrate complex. So at that time the limiting initial velocity is reached maximum velocity. So at initial velocity, your rate equation, that is V naught is equal to K2 into ES. So this is from equation 3. Okay, and maximum velocity is, so V max is equal to K2 into, so your all the enzyme substrate complex is nothing but your total enzyme concentration. Okay, so at maximum velocity, your enzyme, all the enzyme is present as enzyme substrate complex. So enzyme substrate complex is equal to your total enzyme concentration. So Vmax is equal to K2 into E naught. That is your total enzyme concentration is equal to concentration of enzyme substrate complex at maximum velocity. So this is the thing we are substituting here. So equation 8, now you substitute here, that is V naught V naught is equal to, so K2 into E naught is equal to V max into, so S divided by Km plus S. So V naught is equal to V max into S divided by Km plus S. So this is your equation number 9. Finally, since the substrate concentration is usually much greater than enzyme concentration, it is your substrate concentration, initial substrate concentration is much greater than your initial enzyme concentration. So in this equation we can replace this S with S naught, that is, it is a known quantity. So V naught is equal to V max into S naught divided by Km plus S naught. So this is your final equation. 10. This has the same form as the equation derived by the Michaelis and Menten. Okay, so this is the equation derived by rapid equilibrium approach by Michaelis and Menten. Here V naught is equal to V max into S naught divided by Ks plus S naught. Okay, this is the equation derived by Briggs and Haldane by steady state approach. So only the difference is the constant. Okay, the definition of constant. Okay, so here it is Km and here it is Ks. Remaining terms, everything is same. So this equation is also known as Michaelis and Menten equation, and the constant is known as Michaelis constant. So Km is known as Michaelis constant and this equation is known as Michaelis Menten equation. Then the equilibrium assumption is regarded as a special case of steady state assumption when it is your K minus 1 is much greater than K2. So you consider the constant term of steady state assumption Km is equal to K minus 1 plus K2 divided by K1. So if K1 is much greater than K2, then your K2 is negligible. So this term comes K minus 1 divided by K1. So this is nothing but your rate constant, dissociation constant by rapid equilibrium approach. The Km is a Michaelis constant in steady state approach. Then if you plot a graph between V naught against S naught at constant total enzyme concentration, it was found to be a rectangle hyperbola. Okay, graph you will get as a rectangle hyperbola. So from this graph we come to know that at relatively low substrate concentration, your V naught, that is your velocity, increases linearly with increase in substrate concentration. So your V naught is linearly increasing with increase in substrate concentration. So at higher substrate concentration, V naught increases smaller and smaller amount in response to increase in substrate concentration. Finally, a point is reached. Okay, beyond this point, there is no change in velocity with increase in substrate concentration. Okay, so this point is known as maximum velocity. Okay, so after reaching the maximum velocity, if you increase the substrate concentration, there is no change in the velocity, because at Vmax your enzyme present in the solution is totally converted into enzyme substrate complex. There is no free enzyme present in the solution. Three special cases of your Michaelis Menten equation, that is V0 is equal to Vmax into S divided by Km plus S. Okay, you know that. So here when your velocity V0 is exactly off of your maximum velocity, that is V0 is equal to Vmax by 2. So when that, so you just substitute in this equation, V0 is equal to Vmax divided by 2 is equal to Vmax into S divided by Km plus S. Okay, just split out. 2S is equal to Km plus S. So Km is equal to 2S minus S, that is equal to S. Okay, so Km is equal to S. Okay. So when V0 is equal to Vmax by 2, that is here your V0 is off of Vmax. So if you interpolate this, you will get Km. So that is Km is nothing but your substrate concentration. So Km is equal to substrate concentration. And the second case, at very low substrate concentration, your Km is much greater than substrate concentration. So substitute this equation, that is V0 is equal to Vmax into S divided by Km plus S. Here your substrate concentration is much smaller than Km, so it is insignificant. So it turns 0. So V0 is equal to Vmax into S divided by Km. So V0 exhibits a linear independence on the substrate concentration, that is V0 is directly proportional to substrate concentration. So it obeys the first order reaction, okay, at very low substrate concentration. Then the third case is at high substrate concentration. So at high substrate concentration, your substrate concentration is much greater than Km. Okay, so in this equation, your Km is insignificant. So that is your Km turns 0. So you will get V0 is equal to Vmax into S divided by S. So we'll get V0 is equal to Vmax. So V0 is independent of substrate concentration. So it follows zero order reaction. So at low substrate concentration, your V0 initial velocity obeys first order reaction, that is V0 is directly proportional to substrate concentration. And at a high substrate concentration, your V0 is independent of substrate concentration, and your linear velocity V0 reaches maximum velocity, it follows zero order reaction. And when V0 is equal to Vmax by 2, that is off of the velocity, when your Km is equal to substrate concentration. Thank you.